So, hi everyone, and welcome to this month's seminar. It's our second to last one for this series, and I'll put the registration information for the September speaker into the chat in a moment. It's going to be Helena Rapp-Wright, who's going to be speaking on driving sustainable analytical chemistry through education, research, and innovation. And that September talk will be on Friday instead of on Thursday. It'll be on Friday, September 25th. So I'll put the information about that in the chat in a moment. But first, I want to welcome our August speaker, who is Ghada Rabah from North Carolina State, where she's a teaching professor as well as a College of Sciences Dean Faculty Fellow. And she's going to be talking to us about her work in the advanced laboratory and the kinds of skills development that she's doing with her students. So with that, I'll turn it over to you so you can take as much time as you like. And welcome.
Thank you, Michelle. Let me share that. Continue to share. Okay. Yeah, thank you so much. I'm really excited to present about, what is our upper level measurement lab and all the efforts that we've been doing there to introduce some interdisciplinary research opportunities and workforce development and engagement with external collaborators, including some coming from industry. Like Michelle said, I'm a teaching professor here at NC State. I've been at NC State probably around maybe 20 years, and I started engaging with the measurement lab somewhere a little under maybe 9, 10 years ago. And I want to kind of put up front here that this is a class that I co-teach with a colleague of mine here in the department, Professor Stefan Frenzen, who's a physical chemistry professor. So I've been teaching the measurement lab for, 8 to 10 years, under 10 years, and really started engaging into developing this, introducing the interdisciplinary research workforce somewhere over the last maybe 7 years. And it's been a process and iteration on what we started and so on. So I want to start by just giving you an overview of what's going to be all in this presentation. And I want to start my presentation with a little bit of background about what would motivated us to go that route with the development of the lab, and and also what inspired us there. And then I want to give you a little description of the measurement lab course here at NC State and the capabilities of the lab that made implementing this program that I'm describing possible. And then I'm going to describe the aspect of the course related to collaborative project that we refer to as collaborative interdisciplinary cures, and some measurements of impact. This is work that we've submitted for publication, and we're addressing reviewers' comments. So, not necessarily putting all the data out, but there's enough that we can share about the impact that we've observed so far, and maybe some words about challenges and opportunities. So as far as motivation, just kind of quickly run through this. I think everybody in this audience appreciates the importance of undergraduate research. ACS CPT recognizes it as one of the most rewarding experiences, helps develop student skills beyond just technical knowledge. Course-based, specifically undergraduate research, these bullet points from the CureNet that was established somewhere in 2012, I think. And basically, instead of having prescribed experiments, now we're going to give students some more authentic research questions, and so they can do some iteration problem solving in the lab. And I especially like cures that are embedded in required courses, because then you can bring that undergraduate research opportunity to everybody who takes the program rather than allow only those who have time to join maybe a group or do a summer research. Initially, there's a lot more cured in the biological sciences. There's increasingly more cured in the chemistry. There's a nice review that came out in 2023 where people can take a look at different cures in chemistry with distribution in the different classes. There's definitely a lot more in the organic and general, very little still in the physical chemistry labs, and some in the analytical. For the most part, the entire course is usually designated to work towards a shared goal, a shared project. There are a variety of models. I think this is a great review for those who want to look at the different types of cures in chemistry. The other, thing that's on our radar, in addition to wanting to introduce undergraduate research given its benefits to a required class, is the value of interdisciplinary experiences. This is a screenshot from ACS journal about ACS journals. I mean, chemists now work in applications in so many disciplines, and there is increasing recognition about the value of interdisciplinary research. And there are many initiatives at our NC State. There are many initiatives to introduce courses where students are exposed to interdisciplinary topics or courses. Some are developed in collaborations with faculty from different disciplines. And if I do a query with interdisciplinary and chemistry keywords in the Web of Science, and this is certainly an underrepresentation maybe of the number of publications, because a lot of people will not use necessarily the keyword interdisciplinary, even if they're doing that type of research. And finally, professional development skills becoming more and more important and more stressed in the guidelines of ACS. So undergraduate research, interdisciplinary experience, professional skill developments were on our radar as we wanted to do the development of this class or do some iterations to how the class is offered. And so what was the inspiration to the model that we decided to go with? Here I want to tell the story of, what kind of inspired us to go in this direction. Probably somewhere close to 10 years ago, the college organized a mentoring program. It's called the Mentor Ring, where faculty from different departments and different colleges come together in these mentor rings and create connections. And I remember talking to someone and saying, when I just started engaging with the measurement lab and saying, I'm looking for some management system for all the instrumentations and so on. So without much detail, that faculty was the co-director of the senior design program in the computer science. It's like, well, why don't you come and pitch it to our senior design students and maybe they'll help you develop that. So a year later, I went to their pitching session and it was awesome. There were like so many people, from researchers from the university, from companies outside, they were pitching this project to students. And the engineering senior design program at NC State, this is the collaborators come and they pitch these projects and students pick their project that they want to work on. And this is typical for a lot of engineering senior design programs across the country. And later on, I got to look into how these senior design programs came about. And it was through an NSF-funded initiative, Transforming Undergraduate Engineering Education, that brought in industry and academic people to talk about how to improve the experience of the students. So with that, coming from that pitching session, I said, well, what about, what if we do something similar in chemistry? Undergraduate research is a little different than senior design, but the idea of offering our analytical chemistry lab the opportunity to choose topics that they're interested in, maybe environmental chemistry, maybe more materials, maybe more bio, and working on authentic research projects with external collaborators, and with people where they can use their chemistry skills to address research questions that are outside their traditional discipline. So this is kind of the idea of what we wanted to do started. And then, I want to put in a plug of, as we wanted to develop professional skills more recently, and under that time when I was doing the Dean Faculty Fellow, I had the opportunity to bring together in a format similar to the Transforming Undergraduate Engineering Education initiative, some industry and academic collaborators to come together and talk about, okay, what are important knowledge, skills, and abilities of our students that we want to see in our students as they graduate. I'm not going to spend a lot of time on that. I'm just going to show you one more slide about these KSAs, but the work was published in JChem Ed. And ultimately what we wanted, we work towards a second Chem Ed Summit where we want to translate these curricular actions to build sustainable communities of practice, whether it's in the measurement lab, to apply, to bring in curricular activities related to professional skills development, whether in the measurement lab or across the different curricula. And just a shameless plug, this QR code we've been collecting when I go to meetings and during our summits and during a benchmarking full-day symposium that we held at CERMAX to learn about what others are doing in the area of developing activities to develop professional skills. If any of this audience is interested in this conversation and in joining that community of practice, please scan that QR codes and you'll hear from us. But just one piece of information before I talk about the class, I want to share from that Chem Ed Summit what we learned about the knowledge, skills, and abilities that the employers are looking for. And so if you look at these plots, on the y-axis, there's the quality of the knowledge or skill or ability, and on the x-axis, it's its importance, and the circle refers to today, and the cross refers to its importance in 10 years. And we had 73 attending that Chem Ed Summit and responding to that survey. And luckily, foundational knowledge is still the most important, will remain the most important. Quantitative reasoning is extremely important. So analytical and measurement lab platforms, are great opportunities to develop these additional skills and develop these quantitative reasoning skills. As far as skills, no surprises there: critical thinking, teamwork, problem solving. And as far as abilities, one where you see the biggest shift between the circle and the plus, that's becoming more and more important, is flexibility and adaptability. So having students work on projects with no known outcome, with some failures during the step, and the need to iterate and proceed with the work is something that hopefully will help them develop the flexibility and adaptability as they graduate. And like I said, a lot of this work or all these graphs and a lot of the data that came out of the Chem Ed Summit is published in JChem Ed. And the strategic evaluations, that link that I have at the bottom of the slide, is a company that we worked with to run surveys and to generate a lot of these graphical presentations of the data. Okay, so what's the class and how do we run it? It's the Measurement Techniques Lab course is a combination. I'm going to go ahead and put all three. So it's a combination analytical physical chemistry course. Over 10 years ago, before I joined the measurement lab, there was a curricular decision to stop offering analytical chemistry 2 lab and physical chemistry lab. and instead to combine those into what we call measurement lab. So, and it's a sequence of advanced measurement techniques 1 and 2, where the measurement techniques 452 at our institution is required class. And measurement technique 2 is an advanced chemistry elective. So in the same way, there are synthesis lab 1 and synthesis lab 2. So students are required to take synthesis 1 and measurement 1, and then they're required to take an advanced chemistry lab, one of those synthesis 2 or measurement 2. So if students are more interested in the organic synthesis path, they'll take synthesis 2. If they're more interested in the analytical measurement path, they'll take measurement 2. The labs meet weekly, twice for approximately 3 hours each, and then there is one weekly briefing of 75 minutes. There is an earlier part in each one of these courses where students are still conducting some experiments and learning some data analysis skills, and they finish with a final project. In advanced measurement, enrollment, per section, we have 4 sections in the spring and 2 sections in the fall. So we max out at somewhere around 8 to 9 students per section to be, to avoid limitations with use of instruments and so on. With the advanced measurement techniques too, we only have 1 section in the fall and we max it out at 12 students. And so what I'm going to talk about here is implementations that we do during the project phases of these 2 courses. And this is when students are working in the lab or on their projects around 6 weeks for 452 and around 7 weeks for 454. And so the lab capabilities that allow us to do this type of collaborations are listed here. We have your typical gas liquid chromatography, the mix of spectroscopy, absorption, emission, infrared UV vis. We do have an ICP OES, which seems to be one of the most popular instruments for collaborators wanting to send us projects for, and thermal analysis and so on. NC State also has a shared instrumentation facility, metric, and we've occasionally had needs to, so we had a project that used MALDI-TOF and we were able to use that facility, or as often happens in instrumentation lab, if we had an instrument break or something go wrong in the middle of a project, we've been able to pivot to use the GCMS from metric or to submit samples to finish our ICP runs and so on. So given the class setup and the instrumentation and the capabilities, the way we plan this is that I start by sending a solicitation letter to collaborators. And so I reach out to them and say, here's our lab capability, here's a description of the class, the timelines, and so on. And do you have a research question that can be tackled by students within the time frame of the course? Where do the collaborators come from? And very initially, it was really through my network from the instructor teaching the class, talking to people and this is how they start. And then word of mouth, somebody in the College of Textiles say, hey, I did this project with this class and we got good results. I had a former student from the lab got a job and then there was a project that they needed to work on. So he reached out, he's like, hey, Dr. Rabah, can we collaborate with the students on this project? And more recently, in the last couple of years, we've been able to penetrate and recruit some projects from local industry collaborators. And, I think of these projects and these collaborations are win-win for our lab and for the collaborators, because the collaborators often need access to certain instrumentations, but they also have access to skilled chemistry students. And for industry, they can get access to prospective, either interns or job candidates, or in general, they can learn about NC students' capabilities as they graduate and what kind of skills they have. For our students, the idea is they can work as in other cures on projects, and they can get to appreciate the failures and setbacks, and that are really part of our research process. And then by working with collaborators from different disciplines, they really get to have an appreciation of what the different disciplines can offer to solve complex problems. And that really gives also undergraduate students some meaningful project experience that they can talk about during interview, or they can highlight it on their job application. I've had a student who we had an instrument installation from Agilent last year, and I walk in the lab, and this is a student that used to be one of my students. I'm like, well, what are you doing here, Justin? He's like, well, and I went and I applied for this job, and I was telling them about work that I did on this ICP-OES project, and so on. So give them a talking point and opens door, and maybe gives them some confidence more than anything, and helps develop important technical skills. So this is how we procure the projects. Our collaborators have been more with word of mouth, and just to give you an idea of the spectrum of collaborations that we've had a lot of collaborations from colleges across campus, agriculture and life sciences, agricultural engineering. We've had a project, and natural resources, and so on. Like I said, over the last couple of years is when we've really been able to venture with local companies, and they've been, for the most part, smaller companies rather than big pharma or big companies. And we've also had projects where students worked across course peer collaboration. So this past semester, we had a group of students work with a class in environmental technology course to go sample, do some environmental sampling of water, and do some analysis using ICP-OES within our class. And, just to kind of give maybe just titles of some projects and appreciation of the breadth of areas that students have had to work on. Some example of projects from the College of Sciences. I think that trace metal content in water reservoir and coastal fish, probably that was one of the early projects. The next two, these are projects that sometimes if we run short on projects, Professor Franzen, Stefan taps into his research group. He's a research faculty, and he kind of pitches in a research project for students to work on. So we've had also the last two bullet points, for example, are examples of projects that came from within our chemistry department when we needed to fill in a gap, but that people are working on interdisciplinary topics. And where I have the asterisks, these are projects that the student contribution contributed, the student work contributed to published work. Some examples from the different colleges about some of the project analysis of sulfur and cellulose nanocrystals, remediation of industrial and mining waste. Students learned about, different varieties of plants that are developed in this researcher's lab to uptake rare earth elements. So quantification of rare earth elements, and that brought up a lot of learnings from even within chemistry about internal standard calibration and things like that, specific to rare earth elements. And we had projects with from the food science. Our students were looking at different types of. This was a collaboration with food science and material science, where students were looking at different types of filter papers to try to remove various compounds through filtrations from coffee, and so on. Bradley Textiles has been one of our earliest collaborators and supporters, and we've had many projects. Students expand, for example, with the pen additives. Students are learning about carbon fiber and, plant-based material, about fiber spinning and things like that. And sometimes the students get to go and visit the lab facility of the collaborator, or go on a field and sample bring in samples, so they learn about sampling. For example, the swine lagoon sludge, in the project with the environmental lab, the students learned about the chain custody. Really a lot of great opportunities. From the external companies, these are the projects that we've had over the last couple of years. Like I said, usually we've been successful getting maybe one semester, maybe we had two, but for the most part, we have one project per semester. And one of the projects, students got to go, in addition to presenting to the department, they got to go and present at the company to the research group there, their work. One of the projects, I'm trying to see which one of that. I don't know if I have it listed there. Yeah, maybe the one before the last there. One of the students got to go and continue and have a paid summer internship and continue working over the summer on this project. So how do we implement that work? Like I said, we start before the project start, and very early in the semester, or before even the semester start, is where I start sending these solicitation letters and recruiting proposals from faculty. And we start vetting these proposals. We often meet with the faculty and talk about these projects, because, while we want students to be able to work with something very authentic and kind of learn to deal with failure, but we want to know that this is something that will has the potential to work. We can see signals. We can actually gather some data. So there's quite a bit of vetting before the project start, and then right at the start of the project phase, we pitch those proposals to the students, and we post a Google sheet, and we ask them to rank their preference, which projects they want to get in, and we look in first top 3 preferences, and we try to the extent possible to give students their top selections, but we make sure that every group is working with has their instrument for their projects, with no sharing of instruments during the project phase. And then the early period in the project phase of the semester, students work on developing protocols, telling us what materials do they need. And to be honest, usually when we vet the projects and the proposals, we start looking at materials if we need to buy something, so the students are not waiting when they're doing the planning. And so a lot of times collaborators will have a material that they want us to use. And during the planning, we also look at TA assignments, what TAs are gonna help mentor which projects, and we have some guidelines for the TAs. And then we move into performing, where students always start, by running some controls and doing some your test, iterate, and analyze. And at the end of the semester, students will present their work to we send invitation to the department and to collaborators, so they do final presentation to a broad audience. But we started a few years ago to do practice presentations, sometimes once or sometimes twice, definitely once, and it's to really start refining those students' communication skills. And so students present as a group oral presentation, and they submit a final report individually. And at the end of the semester, we collect feedback from collaborators, from TAs, and from students. We have before the project starts, we launch a pre-survey, and the survey development is in collaboration with strategic evaluation company that we've worked with during the ChemEd Summit. For the pre and post, they help us launch and analyze those data. And during the project, the performing phase, we've started over the last also maybe a couple of years to have a journal where the students can have communicate with the collaborator. And so at any point in time, the instructor can look in this journal and see where everybody is. Students can tag the collaborator if they need some material, if they have question about some data, or if they want to troubleshoot, or ask them to meet sometimes over Zoom if there's something that they want to discuss about the project, and so on. And for the oral and final presentations, we do have some rubrics that we give students the opportunity to kind of train on using on some sample. For the written report rubrics, we get them to do a homework at the beginning of 452 where they use the rubric to grade some sample reports, so they really know how they're being graded. For the oral presentation, the rubrics are shared with the students, and they're usually shared with the open audience that we invite to attend those presentations. Again, how do we mentor these multiple projects? This is a heavy load work on the faculty. This is not a lab where you kind of work with the TAs, train them, and then let the TAs lead the lab, especially during the project phase, maybe during the earlier part. And I have to say we have awesome TAs, but the workload is heavy. The mentorship and the number of different projects that are taking place. So the faculty is there, at least during project phase, every lab period, offer technical expertise, troubleshooting when needed, and collaborator communication, really when needed or at the beginning of the project. We try once the lab projects start to make sure that the students are mostly communicating with their collaborators. So the teaching assistants, we mostly need their help. Of course, some students, if they know the instruments, they're familiar with it, they're great resources to help with mentoring. But as far as in general, the TAs help us keep a positive momentum. If they track the journal, are the students progressing? Do they have questions that need to be answered before they go to the next lab? They guide them, did you search the literature for this? And just flag some problems, because it's not a very long time period, and just making sure that there's positive progress. And we make sure that TAs are trained on the projects that they're on, the instruments that the projects that they mentor are using, and so on. Our collaborators mentor our co-mentors. They offer technical expertise in that second discipline and the application. And they do follow student progress, like I said, on their Google Journal. We've had, depending on the collaborators, some engage more frequently by coming to the weekly student briefing, or where students every week they report on their findings for the week and their plans for next week. And some will track the journals and show up occasionally. And some will have Zoom meetings as needed. So they do follow student progress. And sometimes students have had either site visits to learn about various aspects of the material or the other discipline part of the project, or field trips. But the experiments, for the most part, they take place in the teaching lab. I'd say for the most part because, we've had a collaborative project with EPR where students went and used EPR in the researchers lab, and in the coffee collaboration, the coffee preparation and filtration took place in the food science lab. But for the most part, the project takes place in the teaching lab and with collaborator support. What do we track? These are just the general grade distribution. Like I said, both classes have some early part of the course. And I think it's important, especially for 452, to remain not 100% cure, because in the early part of the course, we offer homework assignments where students work on, practice, like I said, writing rubrics, and then we give computer labs where they're training on data analysis skills, and they do some lab experiments where they write lab reports and get feedback. But that final project is, the rubric is what's in red. The final paper, oral presentation, and the Google Journal. Then there's a rubric for the Google Journal that we share with the student. And same for the 454, where there are mostly some worksheets to kind of test some technical aspects of the different experiments before we move to project phase. And project phase is worth around 36% in 454. For the project phase, what we track is, we look at professional skills. We try to see, has introducing this collaborative project help students in improving their interdisciplinary research, being able to use their chemistry skills to work with somebody else from other discipline and address research questions and communicate about them. Can they critically think, evaluate, analyze, support their work with evidence, and work as a team? And we measure that with pre-post survey, but we also ask collaborators for their feedback. And we track communication skills as important professional skills, and through the rubric for the Google Journal. And also collaborator feedback and the oral presentation that has a rubric, and so on. We also, having students publish their work was not a primary goal of the class. We wanted them to, we were tracking the learning opportunities, but a lot of there has been high quality work coming out of some of these projects. And a lot of the project that resulted, there are 3 that resulted in publications. Students have continued to work. They said, I want to continue to work on this over the summer and kind of finish, generating material. Some students choose to work over both 452 and continue in 454. Students have asked if they could use the project to present poster presentations. So there has been some productivity in those areas that we think they're good measures for a good impact. And, looking at our collaboration network and referrals from collaborators that came back consistently to pitch project to us. So the pre and post survey, like I said, we work with strategic evaluation, and they took different validated surveys. And so it's a combination of different validated surveys, but as they explained to me, like they take a whole set of questions related to one construct and use it, and like a whole set to relate to another construct might be from another survey. So they're not completely dissecting those validated surveys. But they identified, there were different survey items, and we address, our target interdisciplinary research, professional skills, critical thinking, problem solving, teamwork. And we did add some questions to see, does this help them with career navigations and preparedness? The N numbers are relatively low for these surveys, but nonetheless, we've been able to get some data where we will see larger effect when students have taken both 452 and 454. And, two exposures appears to produce more consistent changes in the pre-post surveys than the single exposure. We haven't really seen great evidence for supporting career navigation and preparedness. There it will be interesting to see is, I don't know if sometimes the student appreciate or know enough about what they're trying to answer to. We look at collaborators' feedback, like I said, and we also ask them for how did students do as far as communication, their interdisciplinary thinking, and so this y-axis here is just kind of some general thematic presentation. For example, for interdisciplinary thinking, we ask them to what extent do you agree that students demonstrated interdisciplinary thinking, integrating chemistry with broader scientific, technical, societal context. And, for the most part, this is only from the fall. We do have data from this past spring that, we will be adding to this and shows similar results. Maybe the lowest area that they rank, and I mean, it's not terrible, but this is where there maybe most improvement needs to be directed is in quality and clarity of student communication. Like I said, we also tracked impact as far as scholarly engagement. 3 students presented their work at local meetings. There has been 3 publications, an additional 1 submitted and 1 in preparation. One of the projects continued to a paid summer internship. And we've had many repeat collaborations and referrals, and from collaborator surveys, when we ask them, would you be interested to come back and collaborate with us, then they really report a positive experience. And and finally, if I look at some student feedback, really they feel that taught them communication, group project skills that will help succeed at work, confidence in lab skills and networking, valuable hands-on experience inside in a field adjacent with our own. And then, they talk about collaborating really made it feel like, it's finding results for larger purpose. They are working towards an application. Challenges associated with this format, with this program. Really, it's the high demand on the personnel. We have 2 faculty teaching the class. We have, I think I had it there on a slide, but I didn't spend much time on it. We have 1 TA per section. And then we have a lab manager, really helps us with kind of making sure everything is in place, ordering material, waste, getting samples sometimes from collaborators, and just troubleshooting with instruments as needed. And TAs, like I said, we tried to get a lot, and we've had some luck having repeat TAs. But the challenge is that, some TAs will go on RA or will graduate. So you really have to kind of bring in the new TAs and train them. Anyone who teaches instrumentation lab probably has the experience of instrument breaking down, and when that happens in the middle of a project, we've been lucky for the most part, but we've had maybe 2 or 3 instances over the last years where we've had to pivot. So far, these are small classes as far as assessment. The general impression and qualitatively, the data seems like it's been beneficial to students, but the N is small. So as we continue offering the class, we will continue to add numbers, and maybe, we will get to see if other institutions try this approach and add those numbers. Some opportunities at growth, like maybe especially for communication skills and for professional skills. I think making skills and skill definitions more explicit to students and talking to them about, mapping how some of these cure activities map to different professional skills, but really being intentional in telling students that these are the skills we're trying to develop in these types of activities. And we do have consideration to take for 54, the second in the series, to be in the sequence to become a full semester cure. It's there's a lot of background work that tries to get these projects going, and having a full semester will help students maybe take even deeper a dive into some of that material. With that, I want to thank our measurement technique students, really, who have been awesome, and they're always super excited about the final project phase, a lot more so than the earlier parts of the class. Our TAs and our lab manager, who couldn't do it without her, the support of the chemistry department, and we had a small grant from the Office of Undergraduate Research to kind of support doing the evaluation from strategic evaluation. And we've had some awesome collaborators who have really invested a good amount of time to support our students and address their questions. With that, I'll take any questions, and I'll put this QR code there again if anybody would like to connect, whether about learning more about this lab or about learning more about activities that we continue to try to learn about related to developing interdisciplinary and professional skills across the curriculum. And thanks again for the opportunity for me to present this in this platform. I'll take any questions.
Maybe I can ask the first question. I don't know if I missed it, but I was wondering how students get placed into groups and assigned to a project if you try to ask them about things they might be interested in and then assign them accordingly, or if you form groups, like what comes first, the project or the group, maybe?
Yeah, so no, I mean, the part of the idea was to allow students to work in areas that they're interested in. So with that, when we pitch the projects, we launch a Google Sheet and we list all the projects, and we ask students to rank their preferences from 1 to 3. And then we look at all those 1, 2, 3s, and we try to give, to the extent possible, their students' first choice. So sometimes students, if they're people they like to work with, they kind of both agree, let's put our name here. And sometimes they end up working with people that they didn't work with previously in the semester. But it's mostly based on students' interest in the chemistry and the type of project that's, they want to work on.
Go ahead, Jack.
Okay, I finally got it. Thank you. It was a great talk. A lot of questions about the mechanics of the course. So you've got four sections,
Yes.
each with two labs. So you got eight sections that you're having, or eight labs a week. How are you scheduling that?
Yes. So let's say when we have Monday, Wednesday, two sections of 452, and Tuesday, Thursday, two sections. So we have only one lab. So what we do is during the early part of the semester where the students are doing computer lab and lab experiments, we have labs in rotation. So Monday, Wednesday, section A are doing computer lab and students are in the lab, and then they flip. However, we set the cap based on our ability when it comes to project phase. Sections A and B on Monday, Wednesday are going to be all in the lab. So that's why we cap each section at
Yeah.
8 or 9, because we really, when they combine and project phase, the lab is so full and busy.
Yeah.
But they meet, and same for Tuesday, Thursday. So they rotate computer lab, and then project phase, they all come to work in the lab.
But you've got two 3-hour labs. Is one in morning, one in afternoon? Or
Uh, no, they're all 1:30 to 4:15. So Monday, Wednesday, there are two sections. Section A, they do computer lab Monday at 1:30. They
okay,
do
I see. So
experiment Wednesday. And so they run at the same time, but
okay.
So that's why
Okay,
they rotate in the first half of the class and they combine in the lab in the second half of the class.
so in effect, in the project phase, then you have two TAs in the lab at once?
Yes. So
Okay.
for Monday, Wednesday, there are two TAs, and TAs generally end up mentoring 1 to 2 projects, and we try to pick maybe in their research if they
Yeah.
are more exposed to a certain instrument. And both Stefan and I actually are directly, tracking everybody, but sometimes we take direct ownership of one project each. So yeah.
Okay. And then in terms of, so students would choose their project well before the project phase starts. Is that correct?
Yeah, it's actually only like a week before, not well before. Yeah. So,
Okay, so
but
you're
it's
having to
probably a week
prep.
before.
So once you vetted the projects, you're already prepping the material or making sure the materials are there and all that at
We
that
are,
stage.
yeah, even before
Good.
student selections, because we
Okay.
usually say, okay, I have 7 projects pitched, unless the students say, there is this project in my undergraduate research, can work on it in this lab, and there's a reason to pivot to a different project. We work with the assumption that these 7 projects are going to be assigned. So we start prepping for material and for what needs to be prepared for it, because
Now,
otherwise, you lose,
are the
students.
clients, like I know clients will provide proprietary materials, but if there's basic reagents, are the clients providing that, or is that out of your cost of your lab?
Sometimes, I mean, we say we will buy chemical reagents for the projects and as part of our ETF cost. But we've had collaborators that say, okay, you know what, we already have the standards, we have these reagents, we're just going to put them all in a box, and they're local. We're lucky to be
Okay.
in the
Yeah.
RTP. There's a lot of local company. Or if it's different college, we can, me or Alex, our lab manager, will drive over and get the samples. So it's a mix. Yeah.
Okay.
And sometimes if reagents are, like standard reference material could be quite expensive. So if the collaborator has those, they share them with
Okay.
us. Yeah.
I'll let others have a chance for a while, but thank you.
Yeah, John, go ahead.
Yeah, so you're in the Research Triangle Park, so you have a lot of different opportunities to meet with people in industry. How did you sort of get some of those initial meetings set up to think about some of these project labs?
Yeah, so like I said, well, the very first project came from a student who graduated from the lab and took a job locally and said, "Hey, we have a project that might be fit for something that I worked on in the measurement." I think that other projects, they're really started with a personal connection, knowing people in those companies, and for me, it was like you just need to start somewhere and show that your lab can produce positive results, and then you can start promoting those to get more. The larger cohort still comes internally from the university, and this is really through, I'd have to say, word of mouth. We work with the faculty and we say, the project works, and they tell their colleague, hey, you're working on this, see if Ghada has, pitch it to her students, and so on. So it's been a lot of um, just maybe networking. We're putting together a website where we can maybe formalize this more, and we can have, solicitation letter, project proposal submissions, and things like that. I mean, if you go to the engineering model, they get the sponsors to sponsor and pay, like, big money to sponsor these projects and sponsor the department and the program. So, be nice to get to a point where we can get sponsorship for the whole measurement lab program, not to their specific project only. But we're not there yet. We're still really try to reach out and connect. And so we've been increasingly lucky because we've had good project, but it's not trivial yet.
Thank you.
Yeah, Susanna, go ahead.
Hello, thank you for a nice presentation. Just to add to what you said, and maybe that's going to help Jonathan. So I work at primary undergraduate institution, and one of our first partners was a community garden. So if you have a center which does community outreach, they just send an email. These are our capabilities, and so we got Urban Greenworks, which is a nonprofit, and with the analysis of soil for them for heavy metals. So that was a nice project. But I also have a quick question. What are the prerequisites for this course? What's the preparation of your students?
So 452 is usually a spring junior year, and 454 is fall senior year. So by then, students have taken quantitative analysis, lecture and lab. They have taken physical chemistry, and usually the instrumental analysis class is a co-requisite for the measurement lab. And then obviously measurement 2, the co-requisite is 452, which has these prerequisites. But a class of physical chemistry, quantitative analysis, and co-requisite is instrumental analysis.
Thank you.
Go ahead, Chuck.
Or he's just still thinking logistics. So would those same instruments, would students see those in the instrumental analysis course?
So the instrumental analysis is the lecture part of the course.
Oh,
Is
the
that what you're
instrumental is
asking
just a
about?
lecture. Okay.
Yeah, the
Sorry,
lecture is a
instrumentals.
prerequisite because we don't have an instrumental lab. It became
Okay, okay,
measurement lab.
okay.
But during the early part of the instrumental lab, measurement lab, before we start the project phase, depending on the project, some students might have seen the instrument. So you obviously UV vis, HPLC, fluorescence, we run experiments. Sometimes they're working with an instrument that I haven't seen before. So we have SOPs for the different instruments, and we have to kind of show them at the beginning, like thermal analysis.
Yep.
We used to have a regular experiment with the DSC and TGA, but we tried to cut on the number of the earlier. So ICP OES, we don't have a regular experiment. That's usually and you. So there are some projects where they're using instruments that they didn't use previously, but others not.
And one other question. Could you have one project being done by two competing groups, like one Monday, Wednesday, and one Tuesday, Thursday?
We've had that, but we try to have, and sometimes that helps us fill if we don't have enough project. If there is a project big enough where, let's say, they're looking at how different pH conditions or different solvent environments and so on impact the outcome. So we could have a group on Monday, Wednesday look at this aspect of it, and a group on Tuesday, Thursday look at the other aspect, or maybe some vary temperature, some vary pH, and things like that.
Okay, collaborative rather than competitive.
Yeah, we tried not to make them super identical. Plus 454, the students have gone through 452, so we tried to have their projects have maybe a little bit more depth than the 452, because they can handle maybe a little bit more, just a tiny bit.
Okay.
Yeah.
All right, I think we'll wrap it up there. Putting the information about next month's final seminar in this series in the chat. But I just want to thank Dr. Rabah one more time for a really great presentation. I'm excited to look up some of the citations and resources that you mentioned. Thanks so much.
And hopefully, if our manuscript goes through the second rotation of reviews, we'll get to have a lot of the details and the data published in that. But thank you so much for this opportunity. I enjoy very much presenting about this. It takes up so much of my time, and I like sharing this. Thank you.
It's really cool.
Yeah.
All right.
Take
Thanks,
care.
everyone. Happy start of the
Bye.
academic year for those of us who are getting going here.
Yeah. Take care. Bye.
Bye-bye.